Hello everyone, and thanks for watching Edupedia World videos. In this video, we begin a detailed study of semiconductors, starting with the most common one, silicon. Now, we've seen the basic structure of a semiconductor, basic band structure before. The most important characteristics are you have a completely filled valence band at 0 Kelvin and you have an empty conduction band. But the difference between these two, the band gap, for a reasonable temperature is of the order of kT. So as the temperature starts increasing, because of thermal excitations or thermal energy, electrons will often move from the valence band to the conduction band and they will leave a hole in the valence band. A movement of electrons from, say, the left to right can be seen as a movement of holes from the right to the left. Now, this also can be seen in the form of covalent bonds, where you have covalent bonds between the silicon atom. Every atom has covalent bonds with 4 neighboring atoms, and you could actually take an electron, break a bond and take an electron to another bond, and there would be a hole left in this bond. And this is another way we can visualize electrons traveling from one point to another, which is just in a weird perspective what electric current is. Right. Now, in a pure silicon, or what is called a pure semiconductor, the number of conduction electrons are nothing but electrons which conduct electricity. So obviously, for example, even a conductor like sodium has lots of electrons, but only the electrons in the outermost shell in the partially filled valence band are the ones that conduct electricity. Here the electrons that move from the valence band to the conduction band due to thermal excitations will be considered conduction electrons. So the number of electrons in the conduction band, which are also called conduction electrons, is equal to the number of holes. Another way of saying that is the number of positive charge carriers is equal to the number of negative charge carriers. Pure semiconductors are also called intrinsic semiconductors. And because in intrinsic semiconductors the number of electrons is equal to the number of holes, we often refer to the creation and destruction of what are called electron-hole pairs. Which we'll often refer to as EHPs. So every time an electron goes from the valence band to the conduction band, we have a conduction electron created. An electron is not created, remember, but that electron becomes a conducting electron. So now it's called a conduction electron. So every time an electron goes from here to here, we have a new conduction electron and a new hole. So we say that an electron-hole pair is created. Every time an electron moves down from the conduction band to fill this hole, we say that an electron-hole pair is destroyed or annihilated. The creation of electron-hole pairs increases the conductivity, and the destruction of electron-hole pairs decreases the conductivity, and in steady state you actually have the number of electron-hole pairs being created equal to the number of electron-hole pairs being destroyed. Now, the conduction properties of a semiconductor can be drastically changed by diffusing a small amount of impurity in it, and this process is called doping the semiconductor. So, for example, we just looked at a bunch of silicon atoms, each forming 2 bonds, a covalent bond with 4 nearby atoms. Now, what if we introduced in silicon a small amount of phosphorus atoms? Silicon has 4 electrons in its outermost shell, therefore it needs to form covalent bands with 4 other atoms just like carbon, but phosphorus has 5 electrons in its outermost shell. So if this silicon atom was somehow replaced by a phosphorus atom, whereas all the others were still silicon, then you would have the 4 covalent bonds, but you would also have one extra electron given by the phosphorus atom. Now, here's a point I want you to clearly understand. Just because there's an extra electron does not mean there's an extra negative charge. There's also an extra proton which is inside the nucleus, but they never move, right? So, doping of a semiconductor with this is called a pentavalent element, which means it has a valency of 5. That means it has 5 electrons in the outermost shell. So when you introduce pentavalent atoms into silicon, that does not mean that you've increased the negative charge. The total bulk material is still electrically neutral. The number of conduction electrons, however, have increased because this one electron does not have any other atom to form a covalent bond with, nor does it need to, because now the outermost shell of phosphorus is filled. So this electron can actually go on conducting, and we see that instead of an electron hole pair being created, we have one extra electron, not a hole. So when you dope semiconductors, in that case the number of electrons does not need to remain equal to the number of holes. One of them is increased and one of them is decreased. When you include pentavalent atoms, when you introduce pentavalent atoms, then you have extra conducting electrons, and in that case the electrons, which I'll refer to from now as E, become the majority charge carriers. That does not mean there are no holes. There are still some holes. You will still obviously have silicon-silicon atoms as well, but the holes are then called the minority charge carriers. So in pure or intrinsic semiconductors, you always have electron hole pairs. That is, the number of conduction electrons is equal to the number of holes created. But you can actually have one type of conductor more than the other type if you introduce pentavalent elements like phosphorus or any other elements below phosphorus in the periodic table into silicon. Now the interesting thing about this is that this extra electron has an energy level which we refer to as the impurity level, and because all the others have been filled, this electron has an impurity level or the energy level which is just slightly below the conduction band of silicon. So if this was the conduction band of silicon and this was the valence band of silicon, which was, let's say, completely filled, then the extra electron would have an impurity level which would be somewhere here, quite close to the conduction band. So even with a very small amount of thermal energies, electrons from the impurity level could jump into the conduction band and become conducting electrons. So this is how we see even a very small amount, and it's actually very small, 1 in 10 to the power 6 or something, could actually increase the conductivity by a huge amount. Introduction of a very small amount of impurities could actually have a very drastic change in the conductivity of this now impure or also called extrinsic semiconductor. Extrinsic semiconductor. So this is one way to do it, in which you could increase the number of electrons, making them the majority charge carriers, by introducing pentavalent atoms which have an extra electron which has an energy level or the impurity level just slightly below the conduction band. Now you can actually go the other way as well, and instead of introducing phosphorus, you can introduce a trivalent element or a valency of 3 like aluminium. In that case, you would not have an excess of electrons, but you would actually have an excess of holes, because these are the 4 general bonds created by silicon. Now instead of silicon it was aluminium, then you could only create 3 bonds because it only has 3 electrons. But then to balance it out, electrons could come from other already existing bonds here to form this bond, and this would be a way of saying that a hole has traveled from this point to this point. So when you introduce phosphorus atoms having 5 electrons, you make the electrons the majority charge carriers, but once you introduce trivalent atoms, you actually make the holes the majority charge carriers. So now the electrons are minority charge carriers because they are fewer in number, and the holes are the majority charge carriers. the energy of this fourth bond created, or the energy of this hole, which we also refer to as impurity level, is actually just slightly above the valence band. So if this is the valence band which is completely filled, this is the conduction band, then for this case the impurity level is somewhere here. So the electrons that are in the valence band, instead of jumping to the conduction band, which would require more energy, can actually easily jump to the impurity level to fill these holes, and that would create a number of holes within the valence band. No electron has been created corresponding to this hole. Therefore, now the number of holes is more than the number of electrons, and these are called the majority charge carriers. These impurities, which take a hole, trivalent impurities, are called acceptor impurities. And such semiconductors are called p-type semiconductors. Because holes are the majority charge carriers which are positively charged. The impurities like phosphorus are on the other hand called donor impurities, and the semiconductors of this type are called n-type semiconductors. I want to stress once again, p-type semiconductors are not positively charged. They are electrically neutral. It's just that the number of conduction holes is more than the number of conduction electrons. And n-type semiconductors are not negatively charged. They are also electrically neutral. Whenever you add an extra electron due to phosphorus, there is an extra proton in the nucleus as well. But the impurities of the electron, the number of electrons is more than the number of holes, so they are the majority charge carriers, and that is why we refer to them as n-type semiconductors. Now in this chapter we will give you some results which we will not try to derive because the derivation is quite complicated, and one of them is the product of the density of conduction electrons and holes is constant for a semiconductor. So initially, let's say you have n, which is the number of electrons or holes initially, that means n electrons and n holes, then n into n or n squared would be equal to NHNe when it is doped. Whether positively or negatively doped, whether doped with acceptor impurities or donor impurities, doesn't matter. It doesn't matter which is greater and which is smaller. This will always be true. So as the number of acceptor impurities is added, the number of holes will increase, and correspondingly the number of electrons will decrease, such that this result will always be valid. This is also sometimes referred to as Ni, or the number of intrinsic charge carriers. For silicon at 300 Kelvin, the total density of electron hole pairs, that means the value of N, is approximately 7 into 10 to the power 15 per meter cube. So this is 49 into 10 to the power 30. Now if you add some acceptor impurities, the number of holes will go up and the number of electrons will go down, such that the product still remains the same. Also, we started this whole chapter from Ohm's law, which said that sigma is equal to J by E, which can also be written as NeVd by E, which can also be written as Ne mu, where mu is the mobility. We've seen this formula before. So when we're talking about semiconductors, the formula we use is sigma is equal to Ne E mu E plus NH E mu H, where Ne is the number or the density of electrons, mu E is the mobility of electrons, NH is the number of holes, and mu E is the mobility of holes. Also, for a second, let's look at the temperature dependence of conductivity. As T increases, the average energy exchange in these collisions increases, and so the number of electron hole pairs increases. Or another way of saying that would be more electron hole pairs are created. And the mathematical formula is the number of electron hole pairs. We saw that it was 7 into 10 to the power 15 for 300 Kelvin, but as temperature rises, it basically is proportional to T to the power 3 by 2 e to the power minus delta E by 2 kT. We will not give you the proof of this. This delta E is the band gap. And we see as temperature increases, number of electron hole pairs increases, which is basically the reason that the conductivity increases with an increase in temperature, as opposed to the metals or conductors for which the conductivity decreases with decrease in temperature, with increase in temperature. Thank you.